All right, so this video is going to be going over critical numbers and then also using the closed interval method to find absolute maxes and minimums. So if we have a derivative and that derivative is equal to 0 or is undefined, then we are going to define that as a critical point, okay? Now, Fermat's theorem says if you have a local maximum or local minimum, then you must have a derivative of 0. Anytime you have a local maximum or a local minimum, that slope of the tangent line has to be 0, which is true. However, just because f prime of c equals 0 does not mean that you have a local min or a local max. Look right here at like an x cubed graph. You might also have what's called a saddle point, like in the x cubed graph, where you would have a horizontal tangent line, but you don't have a maximum or minimum. However, all the times that f prime of c equals 0 or f prime of c does not exist, we probably have something going on, and there are all kinds of graphs here to show you that. All right, let's do some examples together. So for each of the following functions, find the critical points, and then we could use a graphing utility to look at the extremum of each one of them. So let's look at A first. All right, f prime is 3 times 1/3 x squared, there we go, minus 2 times 5/2 x plus 4. So I end up getting x squared minus 5x plus 4, and I want to know when is this equal to 0. I could factor this into x minus 4, x minus 1, and I get my zeros to be x equals 4 and x equals 1. So those must be the critical points. If we look at a graph of this, let me pull up a little half page here. Okay, then we can look at y equals 1/3 x to the 3rd power minus 5/2 x squared plus 4x, and we can see at x equals 1 and at x equals 4, I do have a local maximum and a local minimum. All right, so let's go ahead and look at B. I have f prime equals 3 times x squared minus 1 squared, and then times the derivative of the inside using chain rule. I'm going to let this be equal to 0. I end up getting 6x times x squared minus 1 squared equal to 0. If I want to find the zeros of this, I get x equals 0. And then I also need to look at where x squared minus 1 equals 0, and that's at x equals plus or minus 1. Those are my critical points. And then let's go ahead and pull up a graph and see what this looks like. Y equals x squared minus 1 to the 3rd power. And I'm going to go ahead and zoom in. Now it looks like here I would have saddle points. Okay, I don't have a relative max or relative min. If I'm coming down from the top of that value and then kind of squiggling through, I'm not going to have a maximum here. I'm not going to have a max or min here, but it does look like at x equals 0, I have a relative minimum or a local minimum. All right, I'm going to do C up in this area here. I didn't really give myself a lot of room for that, but let's go ahead and find f prime. We have low, d high, minus high, d low, all over low squared. And I want to know when this is 0 or undefined. We didn't have that issue with A or B because we didn't have that issue because they were polynomials. But here, I don't actually have any issues of being undefined either because x squared plus 1 is never equal to 0. So let's just look at the top here. Let's see, I have 4x squared plus 4 minus 8x squared. And I want to know, when is that 0? Negative 4x squared plus 4 equal to 0. Negative 4x squared minus 1. And I end up getting plus and minus 1 as my critical points. And again, we can look at a graph. Y equals 4x over 1 plus x squared. And it looks like, yep, I do have a local max and a local min at plus and minus 1. All right, so that's what the definition of a critical point is. Take the derivative set equal to 0 or find where it's undefined, and that's going to tell you something in particular about the graph of f. Now, if we want to find the location of absolute extrema, we still have to have a closed bounded interval based on the extreme value theorem. So that is still true. You still have to have a closed and bounded interval. So notice in our examples here, we do have closed bounded intervals, but we're going to use critical points plus these intervals to do what's called the closed test, okay, the closed interval test. So in this case, I'm going to try to figure out if I have a critical point on this interval. So f prime equals negative 2x plus 3 equal to 0, negative 2x equals negative 3, and x equals 3 halves, which is on this interval. So then what I would like to do is I'm going to look at values on f. I need to look at the endpoint values, and then I need to look at that critical point. Well, if I plug in 1, I get negative 1 squared plus 3 minus 2. I end up getting 0. If I plug in 3, I get negative 9 plus 9 minus 2, so I get negative 2. And to plug in 3 halves, I'm going to actually plug in to a calculator here. So negative 3 over 2 squared plus 3 times 3 over 2 minus 2 gives me 1/4. So I can then see on this interval, because this is the only critical point that I have, okay, so f prime is 0, so that's the only potential maximum or minimum, it's only candidate. I can then see on this interval what my absolute max and absolute min would be, because it's a closed interval, it's a continuous function. And so if I see my lowest value is negative 2, it occurs at 3. And then actually my highest value is 1/4, it occurs at that critical point. Now, if you think about this as a function, it is a parabola that opens down. And we can use the vertex formula to figure out the vertex, x equals negative b over 2a. And we get 3 halves, which is where I have my horizontal tangent line. And so it should make sense on this interval that at 3 halves, that's where I'm going to end up having my absolute maximum. And then 1, 0, really, I should do this. 1, 0 is nothing. And then 3, negative 2 is my absolute minimum, like so. So this is my absolute max. This is my absolute min. All right, let's look at another example. So we have f of x equals x squared minus 3 times x to the 2/3, and I'm looking from 0 to 2. And so let's find the derivative. 2x minus 3 times 2/3 x to the negative 1/3. And I want to know, when is this 0? So let's clean this up. 2x minus 2 over the cube root of x And I'm going to go ahead and make this have a common denominator. So I'm going to multiply this by cube root of x over cube root of x. This should be x to the 1/3 and x to the 1. So I'm going to have 2x to the 4/3 minus 2 all over the cube root of x. And I want to know when this is 0. Well, one thing that I also know is I can't have x equal to 0. That's going to be undefined. So that is one of my critical points. And then also I need 2 times x to the 4/3 minus 1 to be 0. So x to the 4/3 minus 1 equal to 0. X is going to be 1 here. So let's look at our interval again, what we're going to be looking at. So from 1 to 2. So these are my two critical points, x, and then my function values 0, 1, and 2. And so at 0, when I plug in here, I end up getting 0. I'm going to go ahead and write the original function. What was it? So I don't have to keep scrolling back and forth. X squared and then minus 3x to the 2/3. Okay. Now let's plug in 1. When I plug in 1, I get 1 squared minus 3 times something that's going to give me 1. So I get negative 2. And then let's go ahead and plug in here for 2. So I'm going to have 4 minus 3 times the cube root of 2 squared. So 4 minus 3 times the cube root of 4. Now the question kind of is this number a big number? Is it bigger than 0 or is it smaller than 0? And then that's going to kind of help us figure out that value. So when you go to plug it in, it is a number that's going to be negative because it's going to be 3 times, I don't know, something around 2-ish maybe. And so that's going to end up giving me something that is in between these two values. And you can use a calculator if you want to. So that tells me that this must be my absolute max. This must be my absolute min. And let's go ahead and look at a graph of it to just verify what's all kind of going on this function. All right, so y equals x squared minus 3x to the 2/3. And so we can see here, I'm only looking from 0 to 2. I do have a continuous function from 0 to 2. So I can apply the extreme value theorem. And then it's like, okay, well then where do those extreme values occur? You can see that I do have a cusp point. So that is why at x equals 0, my derivative is going to be undefined. But I have a value of 0, 0 on my graph. I have a value of 1, negative 2. And then if you look here, your value at 2 looks like it's pretty close to, yeah. Okay, so something between 0 and negative 2, like we said there. So not an absolute max, not an absolute min on this interval between 0 to 2. So absolute max would be 0, absolute min would be negative 2, and then you can say the x values is where they occur